Hi guys. I wanted to just introduce this talk. As you know, as we're talking about beyond 5G and moving on to 6G, looking back at like what happened in 5G, like what are some of the lessons learned, or what can we do as we go into 6G that could maybe help. So, like one example would be FR2. While it's been in like the iPhone since 2020, and largely it's only been deployed in the US so far. And as engineers, we get very excited about new spectrum, FR3. It's going to be all kinds of new exciting hardware implementations, and then further increase in data speeds. But given at least part of it is that the FR2 hasn't made as much impact to the end user as initially intended. And despite the engineering team solving many challenges of like putting, as Gabriel would say, directional communications in a mobile phone, and then deploying it widely and solving all the engineering problems of coverage, we are able to get 10 gigabits per second peak rates, with 1,000 megahertz of bandwidth, but it's not clear if anyone ever actually uses that, or what applications and things would use it. And as we go into, say, 6G, how would, was partly like, how could we do that? And I guess the other aspect is FR2 is starting to, I think everybody, so far it's only been in sort of premium tier handsets like Galaxies and iPhones, but everybody needs high data speeds. So I think we will, there's some challenges to kind of proliferate that into the mass market, sort of mid-tier phones as well. Although there is some, MediaTek recently launched a Motorola phone that has, their own millimeter wave solution, which I think could help proliferate more of the millimeter wave. But in general, I think there's been even competition spectrum, or spectrum competition. So with C-band in the US being now available, and that allowing higher costs because we need, there's 4 modules essentially for 3.5 gigahertz bands in the phone. So it is becoming more challenging to the end OEM to kind of integrate more and more of these radios at a reasonable cost. So I think that's going to be one of the further challenges as we go to 6G, especially as we continue to add on spectrum and also concurrent use cases. So like one of the biggest challenges from at Qualcomm that we had was that how do we do FR1 plus FR2 concurrently, and how in the future we would incorporate FR3 at the same time. There's really, at least the cell phone is covering from 600 megahertz now all the way up to potentially 50 gigahertz, and then expanding further going forward. And so, FR3, maybe John mentioned like 8 to 24 gigahertz. So that will also, it's not clear what type of architectures we would choose there and for which band. And there's a lot of also, existing networks out there that would require sort of interference cancellation. With that said, my colleague at Qualcomm, Kausik, will kind of show what's the present state of FR2 and how it's evolving, globally. So, thank you.
Thanks. Good afternoon. I had few slides, but before that, I think let's step back maybe 5-7 years. There was no 5G. It was only 4G LTE. And the biggest headache and struggle we all used to have, traffic was almost growing, the demand, the usage, by a factor of 2x per year, almost like Moore's law type of pattern. But the spectrum was limited, and it was extremely costly. So either you improve spectral efficiency or you expand spectrum, otherwise it was not sustainable. Lot of statistics are out there in the field that over last 10 years, the cellular traffic grew by about a factor of 75x. Globally, if you take US or China or specific markets, those increased much more significantly. So then the question came is, how do we even solve that problem? Spectrum is extremely costly. Verizon paid 45 billions to get 100 megahertz. Herein came the story of millimeter wave. Two benefits: abundance of spectrum. Number one, it doesn't even exist for other frequency bands. Secondly, it comes at a fractional price. If you adjust per megahertz of spectrum cost, and that is probably not the right comparison because propagation is much smaller. So if we adjust for the area as well, it's still 10 to 15x lower cost of spectrum acquisition. So both variables are really helping us. Spectrum is there and cost is also less, and we need to meet the demand. Herein came millimeter wave, and probably it is often talked about what is the incremental technological benefit that 5G had introduced. It existed as OFDM in LTE. It is still OFDM. I would like to say we could not even think about going beyond 3.5 gig in LTE. Millimeter wave was unthinkable. It is there, working in your phone, whether you need 10 Gbps yourself or we can distribute across, there is a capacity solution. So it gives you cover, protection, your insurance, probably for next 10 years. It's not a coverage solution per se. It is not going to cover your i5, but where there is huge footfall, extreme high traffic density, in particular uplink, this is unmatched solution. I don't know how to move forward with the slides. Okay, maybe this one. Okay, so having said this, how is it looking like globally? This is a representation of where we stand today in respect of millimeter wave commercialization. Base station, device and all. The most aggressive deployment that happened so far in the US, followed by Japan. You will get pretty good coverage at high traffic density areas, but again it is not for ubiquitous coverage. Few other regions are coming up. Southeast Asia is extremely active, and it is expected that a lot of things will happen next year in India and most likely in China as well. So this is the reality of today, but fast changing, significant adoption happening. Device-wise, there is no issue. Your iPhone, your Samsung Galaxy, all phones support millimeter wave at different price tier. And one new business proposition that came out because of this enormous bandwidth, that even in the developed world, say US, if you go outside big cities, suburban or rural areas, there is something called a digital divide. The cable connection that you have or that people get at their home is not good. It is often very costly, or the cable providers are not that interested because it's pretty far off and isolated. Here comes the benefit of making use of that enormous bandwidth, using in a so-called wireless fiber form, using as a replacement of backhaul. That became a pretty successful deployment model using fixed wireless solution as well, in addition to your iPhone and Samsung Galaxy. And again, the deployment, the way it is happening, it is not really I5 coverage type of deployment. If you are in a Super Bowl stadium and everyone is uploading photos and whatnot, the first thing happens to any cellular technology is your uplink chokes, followed by a snowball impact. And herein comes the beauty. With 800 or 1 gig of spectrum, with whatever split ratio between uplink and downlink, you are well protected. Do whatever you want to do in terms of Facebook upload or other things, you are covered for next 10 years. Right before this presentation, there was a talk, very nice talk around this energy sustainability, significant power saving benefit as well from both base station and device perspective in terms of total wattage consumption, either per megahertz or totality, especially when you use millimeter wave base stations. No rocket science, no black magic here. The EIRP is much less. The targeted footprint is a smaller area. So it paves the way for energy sustainability as well. And I just mentioned about this thing, the rural and suburban, but this is turning out to be an excellent deployment model, both in the US and outside, wherein the fixed wireless terminals are out there, connecting to the base station, either serving to individual homes as a replacement for your cable connectivity, or to the enterprise buildings where optical fiber connectivity is either infeasible or extremely costly. And again, a case study, whether you like it or not, we live in a world where unwanted things happen, or there could be celebration, or there could be extreme high traffic density. Mid-band or conventional frequency bands, it's a limited spectrum and extremely costly. What happens all the time? Uplink chokes first and impacting or creating a snowball impact. If you are not able to reach someone, you try 5 times and everyone does that. So this is an opportunity, again, not across the board, not entire San Diego or Los Angeles, but very high traffic density gives a public safety advantage and traffic offload and superior user experience as well. Now, how is that deployment happening? The right side, what you see is a real base station. And so this is a real lamppost in San Diego. And actually, this is the base station. Each face is representing one sector, and there are 3 faces. Pretty cool, millimeter wave. All 3 operators, major operators in the US, they are following this deployment model, but some focusing on primarily outdoor, some indoor or stadium. By the way, there are 50 Super Bowl stadiums. If you go to any one, and if you are the top subscriber, you do get millimeter wave wherever you are sitting, doesn't matter. And then whether you want Gbps or its capacity, you can make use of that. Moving on, no, it's not just US story. Significant deployment happening in Japan. They are very well ahead in terms of adoption of technology, adoption of new features and capabilities. Their deployment model again at hotspots or at a place of high traffic density. Led by, of course, Docomo, who is one of the leading operators, but others are not falling behind either. Europe, it's still gradually coming up, but it's an example of a city which is called a smart city in Finland. So it's in the backyard of Nokia, and it's a live network. If you are there with your phone or something else, you can test it. It's commercial. India seems to be happening starting next year in a pretty massive scale. And herein comes the point that I mentioned earlier, this new business model around fixed wireless. Some of you might know that it's extremely congested out there, typically unplanned cities. So deployment of optical fiber and reaching out to every home, almost impossibility. So use of wireless fiber, millimeter wave in particular, is turning out to be a priority. And in particular, operators got that spectrum, gigahertz of spectrum, almost freely. Now, how is deployment happening? And this is not a diagram, this is exactly how deployment is happening in the US, Japan, and Europe as well. That operators are starting with a co-located deployment. You have a tower where your LTE or 3G base station is already there. On top of that, they are putting a massive MIMO or mid-band base station and a millimeter wave as well. That is step one, followed by a densification which is already happening, say couple of blocks. This is my targeted hotspot, lot of people, lot of traffic. I want ubiquity of coverage so that millimeter wave can offload my congested network. At co-located deployment, there is a slight difference getting into little bit more details. All the millimeter wave products are so-called, today there is no one single box base station, a split architecture. Typically a RAN split architecture type 2 is what millimeter wave does, vis-a-vis non-millimeter wave, they follow a different architecture. So though combining the two, the deployment is happening today in a so-called dual connectivity manner, where anchor lies with this path and millimeter wave is the data pipe. But the densification means the sites are not co-located. And so these are physically two different locations, one base station and a different base station, and they are connected logically, not necessarily direct fiber, to serve the user. Once again, the control connectivity with FR1 and data plane is with FR2. So the lessons learned, I think one thing was fundamentally different, and it took a while to make the industry understand and act accordingly. Historically, if you go back from 2G days to until 5G mid-band, we followed a so-called out-to-in model. You have a tower outside transmitting signal, and that is giving you coverage while you are inside your home as well, in addition to your home Wi-Fi. In millimeter wave, that model is not that easy to make work, primarily because of higher frequency, higher penetration loss. You may get coverage, may not. So the mindset should be different. It is out to out, meaning outdoor base stations are for outdoor hotspot, indoors are for indoor, while you are using your smartphone. or otherwise the fixed wireless terminals are out there. And associated with that, there are other differences in terms of EIRP and how the technology works. Reality also is that we need to be mindful of foliage loss and additional hand and body losses. Those are higher. And you can measure yourself estimated coverage while using your smartphone and you are holding in your hand could be in the range of up to 350 meters. So far so good. Adoption is pretty good. You can use it in the US, in Japan, in parts of Europe, and other countries are coming up. And technology is not standstill. Significant 3GPP evolution or otherwise non-3GPP product evolution is ongoing, and we expect to see further adoption in coming years. And often there is a debate that, oh, this technology doesn't work because it doesn't give you coverage like 700 megahertz frequency band or 850. No, it is not for that type of solution. It is for capacity offload, and if there is one common theme around the globe that stays minus China is spectrum is a scarce resource. Even if you pay billions of dollars, there is no spectrum that is free. Millimeter wave is a spectrum that can help you offload capacity, is doing so. So it is also a cover, a protection for your future, probably for next 10 years. So that was last slide. Any question?
So I thank you for the overview and outlook for the rest of the world and how millimeter wave is shaping up. So I guess perhaps when many of us have read, Verizon has stopped obviously millimeter wave deployments, right? Perhaps you can comment on that. More to the point, I think there are a lot of studies on reliability, right? And the reliability is less than 0.5% for millimeter wave connectivity for 5G, right? At least some reported numbers online I have seen, right? Perhaps you can also comment on those two. I was sort of surprised to not see reliability in your slides, but yeah, maybe there is something different way to think about it, yeah.
Okay, thanks. So first, Verizon decided to stop deploying millimeter wave. I'm not aware of that. On the contrary, my understanding is if we have to follow their last quarter executives' messaging, they are committed to millimeter wave. They are going to go ahead with the same pace as 2022 or even faster to roll out millimeter wave. So I don't know whether that statement is correct. Most likely it is incorrect if we have to go by their executive stance. And not Verizon, but another operator, and they already started having challenges with mid-band, uplink, CPE, capacity crunch, and probably in 2023 you will see a significant push around their millimeter wave deployment as well in the US. The second thing is the reliability. Yes, reliability is a function of multiple things. So 2-3 things. One is I have to have coverage to make the data plane work. That's number one. If there is no coverage, then yes, millimeter wave is not going to work. And the number that has been quoted, this is primarily driven by I am driving on I-5, I don't have millimeter wave coverage, but if I am at hotspot, it looks pretty good. The second angle to that is beyond coverage is what happens to the reliability of the control plane. Data pipe is fine, we have HARC, we have other error correction schemes, but in the control plane it is always challenging. So far the way the deployment happened is control plane to be carried by either LT or by FR1 in a so-called ENDC or NRDC dual connectivity mode. But it is expected that in 2023, we will start seeing pretty significant deployment of FR2 only, self-reliant. I am not dependent on anybody. Connectivity starting with fixed wireless first, and probably towards the end of next year, even with smartphone. One variable will continue to remain is there enough coverage, and what is my deployment model? It is not for ubiquitous outdoor coverage. It is not necessary for that because it is a capacity offload solution, not ubiquitous coverage representation replacing 700 megahertz band. So as long as that is addressed, reliability piece in terms of technology, the control plane as well as data plane, those things are already taken care of, and we are fairly confident it would work stationary with fixed wireless as well as pedestrian and vehicular mobility with your smartphone.
Farshid Pisam. So the cost of deployment will be one of the things that carrier will look at basically for expanding FR2. And you, as representing Qualcomm, do you think anything is within your jurisdiction that you can actually help with that?
Yeah, excellent question. So, so 2-3 things without getting into numbers. So what does cost of deployment include? So it depends on that. If you say that the spectrum cost of spectrum acquisition is part of that, then starting point is Verizon paid $45 billion. It's public information for 100 megahertz of mid-band spectrum. Vis-a-vis millimeter wave was fractional. So you need to take that into account for your capex calculation. But that aside, the base station pricing, without getting into any specific details, compared with a 100 megahertz mid-band massive MIMO base station, vis-a-vis 800 megahertz millimeter wave base station, it's order of magnitude lower, at least 3x lower pricing, depending on which part of the world you are at. So I am not adjusting for spectrum. 100 versus 800, I am comparing 1-to-1 without adjusting for spectrum. Still it is about 2 to 3x lower. But there is one thing though, that the slide I had shown that there is a need for densification. So on the lamppost you have to put like the photo I had shown. One question might come at that lamppost, how do I connect the backhaul? Because that base station to transmit, there is a need for backhaul. And if it is 800 megahertz of spectrum, I need pretty strong backhaul, which will have to be optical fiber. So yes, cost of backhaul, incremental cost of backhaul, which also contributes to capex and partly opex, is an adder, but all inclusive because spectrum pricing is not there and the base station pricing is much lower. The TCO, total cost of ownership, actually is much lower even if you do not adjust for bandwidth. Having said that, although it is not a pricing problem, this backhaul availability of fiber or making it available at every pole is a time-consuming problem statement. It delays the deployment. So there had been a thrust to find out, can we even use part of this millimeter wave spectrum as well as backhaul to connect to the nearest tower, bypassing this optical fiber deployment and expedite the rollout. TCO perspective, it is already better off.
Qualcomm. I recently heard that in South Korea, 2 of the 3 main wireless operators, they initially got the millimeter wave spectrum license, but due to the lack of their investment or spending, the government canceled their license, and I just wonder if you have some insight on what happened.
Yes, that is that's a news that had come out because 2 of the 3, and the most important still has that license. 2 2 of the 3, they did not meet their regulatory requirement. So they still have 1 month, and after that, that license might go away. But the biggest operator there, they still have it, and they are rolling out, that we know. So to be seen how it happens. I think what happened was they got extremely busy with their mid-band deployment. They wanted to make it ubiquitous, one-to-one with their LTE deployment. That kind of delayed their millimeter wave adoption, but the biggest party, they still have the spectrum.
Gabriel Rebez, UCSD. You have not discussed millimeter wave for fixed wireless, to the homes. Not the mobile, not the things you're talking about, but more point-to-point fixed wireless. Yeah, exactly. So maybe this is an example of fixed wireless. So can you give us your opinion on fixed wireless deployment as compared to, small cell or mobile, typical mobile requirements?
So these turned out to be, as I briefly mentioned, these turned out to be a pretty viable and profitable business case for operators in the US at least, and for at least one operator in Japan. What is happening, to take US example, that suburban and rural areas, the cable connectivity is not good. So the same base station transmitting same millimeter wave, you can use your iPhone or your Samsung or something else if you want to use your phone. But a completely complementary solution is a fixed wireless unit to be given to you by your service provider, could be Verizon, could be somebody else. You install it by the window, you get the millimeter wave signal, that is your wireless backhaul pipe. The other end is Wi-Fi that is covering your entire home. So whether you want Netflix or you want multiple Netflix, Amazon Prime, whatever else you want to do, a thick pipe is there which is taking care of your backhaul connectivity requirement. So this turned out to be a fairly beneficial business model being deployed by Verizon and multiple Midwest operators as well. And it seems to be successful. Technologically, there is no issue. Even business-wise, it is a successful thing.
Yes, this is Yang Zhen from PSMI.
Sorry, go ahead.
Okay, the question is, earlier I was surprised to hear you mentioned the power consumption for millimeter wave is actually lower than FR1 or mid-band, I forgot exactly. Could you elaborate on that? What do you mean lower power consumption? Is it for UE or fixed wireless or base station or the entire system? Or was it normalized to per bit transmission? Yeah. Thank you.
So my statement was more about the base station. So a typical massive MIMO 100 megahertz base station today, when it transmits at full power, peak capacity, that consumes in the range of about 2.5 kilowatt, a 3-sector base station, 100 megahertz, vis-a-vis a millimeter wave base station, say 800 megahertz, the photo I had shown, something like this, which has 800 megahertz, 3 sectors, its consumption is around 1 kilowatt. And there is no surprise here, because the massive MIMO base station transmits at a much higher EIRP to the tune of 75 to 79 dBm. Vis-a-vis this millimeter wave base stations transmit at a much lower EIRP, about 54 to 62 dBm range. I think I had a slide. And yes, this is what I was trying to highlight, that if you look at these numbers, these actually contribute to the delta in terms of power consumption. So I'm not adjusting for spectrum bandwidth per se, it's the base station consumption itself.
So you meant base station to base station, single comparison,
Correct,
regardless of area or megahertz.
exactly.
Thank you.
Just very quick.
Yeah.
Sorry. So I mentioned here, we talk about energy consumption, energy efficiency in this section. I'm just wondering your view on this digital beamforming's future outlook at FR2. I mean, how efficient that will be in your mind compared with the hybrid beamformings in terms of FR2 application? The second question is for the, let's say 4 or 5 years down the road, what is your view compared with FR2 and FR3 band as more emerging technologies? In my view, I would see the FR3 would have, realistic speaking, a strong competitions in terms of deployment for FR2. I want to get your points on that.
Yep, thank you. Very good question. So let me see. So the first one is, if I go back 3 years and draw a curve up to today, there had been significant improvement to energy efficiency already, to the tune of where we used to be 3 years back, we are about 35 to 40% lower in terms of base station energy consumption, and we expect it to go further down the line over next few years. So some of the numbers I quoted, those will be better next year and even better the following year. So we are not at the equilibrium point yet. There are opportunities to improve the efficiency. Second one, FR3, the way it is trending, FR3 is an excellent solution, and probably John Smee, one of our colleagues, he presented earlier today. We are trending towards 6G solution for FR3, whereas this FR2 will continue to be 5G and then transitioning to 6G as well. So they are expected to coexist. FR3 propagation will be better than FR2 because of the frequency band of operation, but again capacity will be higher in case of FR2.
So again, a question from me, which by the way, I'm a big fan of millimeter waves, of course, for good reasons. And I can tell you that we are using it in certain areas that we cannot talk about much, very well, and it's working very well. But we really don't talk about these areas much. And it's working extremely well, making some people very happy. And of course, because of the 800 megahertz bandwidth and because of the directionality and all of these things. There are some people who say that millimeter wave inside stadiums and shopping malls and high density areas, will have a serious competition from Wi-Fi 6 and 7 and, all of these, let's say 5 to 8 gigahertz standards, which are all coming very strongly too. And I would like your opinion on that.
So I have 1 minute to wrap up as requested. So let me try.
15 minutes late.
Okay, sorry about that. So to quickly answer that, I take only one example of a stadium. Super Bowl, last 10 years, Wi-Fi traffic grew by 100x, cellular traffic grew by about 90x, 75 to 90x. So the point I would like to make is it is not a matter of your technology versus my technology. Traffic is growing. It went up by 200x almost. So we need all technologies, all spectrum, every hooks together to support that, because it is not going to stop. It is going to go up even further. So there is an opportunity to coexist, which we do see. Wi-Fi will grow, millimeter wave will be there, and will continue to meet the demand for ever increasing growth. Thank you.
Thank you.